Hi everyone, I'm Claude from AI Redefined. In this short video, I'll cover the key points from a presentation I recently gave at Hub Francia during a panel titled When AI Meets Simulation. This panel also included fellow engineers and researchers from EDF, MathWorks, and Extrality. Simulation and data-driven approaches to machine learning have well-documented shortcomings. I'll go over how they can be partially addressed through reinforcement learning, and then share with you how our team, in turn, overcome the limitations of reinforcement learning itself with a novel approach that places humans at the center. Both simulation and AI aims at supporting humans with decision-making. Let's take air traffic controllers, people who make life or death decisions every day. When they dispatch planes to runways, they need to consider the status of each flight, the status of each runway, upcoming traffic, fuel consumption, evolving weather, and so on. This is a lot. Let's see how they could get assistance. One approach is to support them through simulation. Simulations encapsulate the knowledge and experience of humans in pieces of software able to simulate how a system can evolve depending on environment and settings. Simulations can be used to safely explore the outcome of decisions. Let's go back to our air traffic controller friends. Simulated airport and surrounding airspace could calculate an answer to the question: what if we tell plane A to wait 10 minutes and get plane B to land first? The ability to predict outcomes greatly improves the quality of decision. It can even enable to plan a course of action toward a specific goal. But building a simulation is particularly tricky and costly, making it faithful to a particular airport even more so. Running a simulation itself is often costly and long, making them too slow for real time. That's why simulations are often used offline in the design of systems, but are seldom used for day-to-day operations. Another approach is to look at data. The truth is in the data, they claim. A predictive model can be trained from a real-world historical dataset to efficiently predict outcomes of the decision that makes sense in a given context. I say make sense, I should say are usual, as these approaches are about matching the current situation to patterns identified in the historical data. They are not about finding the best decision. If we were to ask a predictive model the same question we did to the simulation, it could predict that with the current load and with the current weather, making plane A wait 10 minutes will be okay. But only if similar occurrences exist in the historical dataset. Training of predictive models can take a long time and be data hungry. However, running the model, the inference part, can be a few orders of magnitude faster than simulation, making this a good fit for real-time use cases, so long as there is a large amount of representative historical data available and that they don't need to adapt to new conditions. Reinforcement learning, RL in short, promises to combine a simulation's ability to explore and plan towards an objective with the operational speed of predictive models and the capacity to leverage observation from the real world. It's a simple idea. An RL policy can generate its own data by trial and error, trying to reach target goals in a simulation. If provided, historical data can supplement RL-generated data, which enables the policy to train continuously in said real world, as it does in the simulation, and to adapt much faster. To our airport landing question, a well-trained RL policy could, for example, in real time, recommend an optimizing landing order to minimize fuel consumption, with everyone landing safely and on time. The trained policy would remember how to reach its goal from the current context and from its past experience in the simulator and in the real world. However, and you'll see a pattern here, training an RL policy can be costly, even with a fast simulator, as training for simple tasks already requires millions of data points. Because the policy has the autonomy to find creative solutions, it can go down fruitless paths during training and can lead to undesired outcomes if the objectives are not well defined. Whether it's simply dangerous, or on the flip side, too cautious to seize optimization opportunities. With simulations, data-driven approaches, and even RL, humans are never involved in the system that represent their environment. They are either on the receiving end, getting recommendations, or offline, involved in the design of the simulations or training process. Think about this. Our air traffic controller, the real expert, is reduced to a passive participant in an imperfect system. To address shortcomings of previous approaches and foster the trust between humans and the AI that assists them, it is necessary to create a positive interaction loop between both. That's how we envision humans in the loop, HITL at AIR. Want to help an untrained RL policy explore more efficiently in the simulation and get better, faster results? Let a human expert guide the exploration, providing demonstration or adapting the task to the AI's proficiency. Objectives defined ahead of time are complex to balance and can be too limiting or not enough. Enable human experts to give feedback to the learning AI on a case-by-case basis. In the safe space of the simulation, human guidance dramatically improves training time, yields better results, and helps associate future users of the AI to its success. Once deployed operationally, this AI will be able to collaborate with humans more effectively and will continue to learn. The way the air traffic controller follows or not recommendation from the AI will help it learn how to be better or when to let the human be in control. This continuous improvement loop also benefits humans, both parties learning to work together and leverage their strengths. Such hybrid systems are a game changer in the development of decision-making assistants. But they imply a lot of moving pieces: simulators, interfaces to live systems, AI frameworks, user interfaces. That's why we developed Cogment, an open source platform to build, train, and operate AIs in environments shared with humans. Cogment provides a framework to make multiple actors, AI agents and humans alike, interact with the simulated and live environments. Actor implementation can leverage any flavor of AI, RL, ML, plain old AI, and any user interface medium. More importantly, actor implementations can be swapped at any point during the lifetime of an application, making it possible to test and combine different approaches. Cogment aims at solving the engineering challenges of humans in the loop approach. It is tech agnostic, C++ ready engines, Fortran numerical simulations, Python RL policies, and JavaScript web app, and more can all interoperate through Cogment. Another key engineering challenge to scale an AI project from an experiment on a laptop to a cloud deployment is distribution. Cogment is distributed by default, and its tooling helps you grow your project smoothly through all these phases. Finally, Cogment is open source. AIR also offers enterprise support and collaborate with its customers on developing the next generation of AIs using Cogment. To give you an idea of what's possible, here are 3 examples of Cogment-powered applications. On the left is a testbed for collaborative and competitive AI agents development. We use it to experiment with multi-agent social intelligence. In the middle is a collaboration with the city of Hong Kong to develop AIs helping with 911 dispatch. The general idea is to adapt the autonomy level of the AI dispatcher to the criticality of the emergency and the cognitive load of the human dispatchers. On the right is an example of man-machine teaming, developed with French aerospace and defense company Thales. The goal is to have unmanned drones collaborate with human pilots during recon missions. As we saw, the interface between AI and simulation is key. AIs need to go beyond simply mining and repeating past data. There is a limit to the use cases stochastic parrots can tackle. Leveraging fast and faithful simulations and involving humans are needed to create a new generation of AIs that can optimize, be creative, and work in synergy with humans. Thank you.